Let's say we are given these 5 rectangles that are all identical or congruent. What fraction of the square is covered by these 5 rectangles? This problem is taken from the book Geometry Puzzles in Field Tips by CATRIONA Shearer. Let's begin solving this problem. It took me more than an hour to figure out how to solve this problem. My first impulse was to represent the length and the width of the rectangles in terms of variable a and b, and represent the area of the rectangle and the square using those variables. But no matter how I simplify those expressions, I still arrive at an answer that is in terms of those variables. What we want to know is to get an exact number that represents the fraction or the percentage of the square that is covered by the 5 rectangles. I eventually find the solution by looking at this main question. What fraction of the square is covered by the 5 rectangles? The key insights that we can get here is we want to know what is the area of the rectangles in terms of the area of the square. So that means we can let the area of the square to be 100%, and therefore the area of the 5 rectangles would be a certain percentage out of 100%. This is very self-explanatory, but the main idea here is instead of me representing the area of the square as some expressions, I will begin by stating that the area of the square is 100%. So let me show you how that strategy works. So let's begin by stating that the area of the square a sub s is equal to 100% or 1. And this is in terms of a square unit. Now, knowing that the area of the square is 1, the side of the square must be equal to the square root of the area, and the square root of 1 square unit is 1 unit. Now, from the figure, let's represent this longer side as our b, and let's represent the smaller side as our a. That means the side here is also b, and this width of the rectangle is a. That means this length of the rectangle is b, and this width is a, but that width is just the same as this width, so this is also a. So clearly from the figure, we know that the side, which is equal to 1 unit, can also be represented as the sum of this length of the rectangle, which is b, plus this width of the other rectangle, which is a. So therefore, 1 unit is equal to a plus b. We're going to remember these values later on. The next thing that we're going to do is find the length of this hypotenuse. What we have here is a right triangle. How do we know it's a right triangle? Because we have a square, the angle here must be 90 degrees. This is a square, so this triangle that we form is an isosceles right triangle. The height is a plus b, and the width is also a plus b. We need to know what is the length of this hypotenuse. Notice that this hypotenuse is composed of 3 parts. One is this part here, the other part is this length, then we have this length of the rectangle itself, and this part here, which is the same as that other part here, and finally this length here. So we need to find what are those values. So if you let the hypotenuse to be equal to c, then c is equal to, we already know what's the length of this rectangle, that is b. Now, what is the length here? What is this diagonal? That is the diagonal of a square with a dimension of a by a. And we know that the formula for the diagonal of the square is equal to square root of 2 times the length of the side a. And so you have here square root of 2 times a, but there is also another part here that is identical to this diagonal. This is another square root of 2a. Putting these two together, this is equal to 2 square root of 2 times a. Next, we need to know what is this distance. Let's zoom that triangle out here. We want to know what is this height. But we know what is this distance. That is the width of the rectangle, which is equal to A. Since this is an isosceles right triangle, this line segment is the perpendicular bisector of the opposite side. And so from this distance going here, that is 1/2 of A. So that is going to be A over 2. Again, this is 90 degrees. This is 45 here. And therefore, this part here must also be 45 degrees. So that means this triangle here is an isosceles right triangle where this side and this side each face the base angles of the isosceles triangle that are equal. So these two sides must also be equal. And so if this one is A over 2, that means this height here must also be A over 2. But there are how many A over 2s are there? We have one here, and we have another one here. So together, that is 2 times A over 2, which is equal to A. So therefore, this hypotenuse C now therefore is this length, which is B, 2 of this here, which is this 2 square root of 2A, and this one plus this one, which is equal to 2 times A over 2, or A. So therefore, we have here plus A. This is now the hypotenuse, and the measure of each leg is A plus B, and the other one is also A plus B. But we know that A plus B is equal to 1. That means we can now use the Pythagorean theorem. Now the next step now is to use the Pythagorean theorem to set up an equation that hopefully we can use in order to solve for the values of A and B. So here, the square of the side, and we know that the length of the side is A plus B, which is equal to 1. So basically what we have is, we are going to square 1 squared, plus, so this is 1, and we square it, plus the square of this other side, which is also 1 squared. This is equal to the square of this hypotenuse, which we already know to be B plus 2 square root of 2 A plus A. 1 squared is 1 plus another 1. This is equal to 2. And notice now here that this A plus this B together would result to A plus B also, which is equal to 1. So we also have here 1 plus the remaining expression 2 square root of 2 A all raised to the second power. Now let's square the right side. This is a square of a binomial. So the right side would be equal to the square of the first term is 1 squared plus twice the product of the first and the second term, that gives us 4 square root of 2 times A plus the square of the second term, which gives us 8A squared. This is a quadratic equation which we can rewrite in standard form. So subtract 2 from both sides to get 0 is equal to, and then let's rearrange the terms here, 8A squared plus 4 square root of 2A minus 1, because 1 minus 2 is negative 1. This is now a quadratic equation that we can solve using the quadratic formula. So in the next slide, let's solve this quadratic equation. So what we want to do is solve this quadratic equation, 8A squared plus 4 square root of 2A minus 1 equals 0. Solve for A. So solving now for A. So using now the quadratic formula, our roots are the negative of the coefficient of the second term plus or minus the square of the coefficient of the second term. So the square of 4 square root of 2 is equal to 32 minus 4 times 8 times negative 1 which gives us also positive 32, all divided by 2 times this 8 to get 16. So this simplifies to negative 4 square root of 2 plus or minus the square root of 64, which is 8, divided by 16. And so we arrive at negative square root of 2 plus or minus 2 over 4. And since we are talking here about measurements of lengths, we are going to rule out negative values and just accept the positive answer. So we will just accept negative square root of 2 plus 2 over 4 as our answer. So let's remove the negative value. So our answer is only negative square root of 2 plus 2 over 4. This is the value of A. That means this small width here is equal to this value. Now, to find the value of B, we know that A plus B is equal to 1. Therefore, B is equal to 1 minus A. But since A is equal to that, we have 1 minus negative square root of 2 plus 2 over 4. And simplifying this becomes 4 plus square root of 2 minus 2 all over 4, which is equal to 4 minus 2 is positive 2 plus square root of 2 all over 4. So this is now our value of B. This is B. So the area now of the small rectangle is the product of A times B. And so we are going to multiply these two expressions. First is, we can rearrange this as 2 minus square root of 2 over 4 multiplied by 2 plus square root of 2 over 4. Notice that these are conjugates, and the product of this resulted to 1 over 8. Now, knowing that the area of the rectangle, this yellow rectangle, is 1 over 8, so at this point, we now know that the area of one of these rectangles is 1 over 8. So the area is 1 over 8. And there are how many rectangles like that? You have 1, 2, 3, 4, and 5. There are 5 yellow rectangles whose area is 1 over 8. So therefore, we can now replace this by, this part here by that value. So the area of the 5 rectangles would be 5 times 1 over 8. And the area of this square, we let that to be equal to 1. So we can now replace this 100% by 1. So this is equal to 1. And so 5 times 1 over 8 is 5 over 8. Divided by 1 is still the same answer, 5 over 8. So for our final answer, the area of the 5 yellow rectangles covered 5 over 8 of the entire area of the square. If the length of segment AB is 4 square root of 10 units, and the side lengths of the 3 squares are consecutive integers, what is the total area of the 3 squares? One of our followers, Dexter Amador, requested that we create a video explaining this math problem. Several weeks ago, one of our followers, also Julia Roldan, presented a video explaining this lesson during one of our weekly math programs. So in response to Dexter, we are sharing this video again. So let's analyze our problem together. It is given that the length of segment AB, this is segment AB, is 4 square root of 10. And we are given here 3 squares, and the length of the 3 squares are consecutive integers. What do we mean by consecutive integers? Examples of consecutive integers are, let's say, 5, 6, and 7. the difference between two consecutive integers is always 1. 7 minus 6 is 1, 6 minus 5 is 1. Now, since it is given that the side lengths of the three squares are consecutive integers, and we do not know those side lengths, we can let the side length of the shortest square to be x units. And if the side length of the smallest square is x, and the three lengths are consecutive integers, then we can let the second square to have a length of x plus 1 unit, and the side length of the largest square among the three to be x plus 2 units. So the side lengths now are x, x plus 1, and x plus 2. These are consecutive integers because the difference between consecutive integer here is 1 unit. X plus 1 minus x is 1. X plus 2 minus x plus 1 is also 1. We want to find the total area of these three squares. So the idea here is, if we can find the side length of the smallest square, which is x, then we can find the side lengths of the two other squares. And when we know the side length of the square, then we can square it to find the area. So we need to find the value of x. Now let's extend this side, and we have this dashed line. If we know that this length is x units, and this length is x plus 1 units, then it follows that this length here must be the difference of x plus 1 and x. And the difference between x plus 1 and x, you have x plus 1 minus x. So x minus x is 0. The answer is 1. So we now know that this length here is 1 unit. Now, let's extend also this side. Since the side length here is x, it follows that this length also is x because we have a square. And this length also must be x. We know that the side length of this largest square is x plus 2. So this length is x plus 2. That means this part here also must be x plus 2. And from here, going to this part is x. And from here, going to this side is x plus 2. That means the length here must be 2 units. Because we have x plus 2 minus x is equal to 2. Or if you add, this length is x, this length is 2. Together, the length of this largest square is x plus 2. We need these values later on, so let's remember this value. This must be 2 units. This length here must also be 2 units. Next, let's extend this side up to this part. We already know that this length is 1 unit. That means this side length here also must be 1 unit. And since we know that this entire length is x plus 2, if we subtract this part, which is 1 unit, then from here, going here, must be x plus 2 minus 1. And what is x plus 2 minus 1? That is x plus 1. So we know from here, going to this part, the length is x plus 1. It follows therefore that this length is also x plus 1. Then let's create now these two triangles. This red triangle and this green triangle. So what do we know about these two triangles? First, we know that AD is congruent to side CE. Let's trace those sides. This is side AD and this is side AE. How do we know that they are congruent? We know that the length of side AD is x plus 1. And we know that this length here is x units and this length is 1 unit. If you combine these two lengths, that is x plus 1, which is also this length here. So that means side CE is also x plus 1. Since both of them are x plus 1, and when the two sides are equal, then the two geometric figures are congruent. So side AD is congruent to side CE. Now, look at this angle ADC. That's a right angle. And this angle CEB is also a right angle. Therefore, we can now claim that angle ADC is congruent to angle CEB because all right angles are congruent. Then let's take a look at these two parallel lines. This line is parallel to this line because we have a square. The two opposite sides are parallel. This line segment AB is a transversal cutting these two parallel lines. And since we have parallel lines cut by transversal, it follows that this angle ACD, and this angle CBE, are corresponding angles on one side of the transversal, are congruent. And so we can now say that angle DCA is congruent to angle EBC. So at this point, we now have a side congruent to another side of the other triangle, an angle congruent to another angle of a triangle, and another acute angle congruent to another acute angle of another triangle. What we now have is a side, an angle, and an angle. And by the side angle congruence, we now conclude that triangle ADC is congruent to triangle CEB. The red triangle is congruent to the green triangle. It follows that from CPCTC, corresponding parts of congruent triangles are also congruent, then side AC, which is the hypotenuse, must be congruent to side CB, which is also the hypotenuse of the other triangle. We know that the length of segment AB is given to be 4 square root of 10. But this 4 square root of 10 is composed of two line segments, AC and AB. So we now have this equation: the length of segment AC plus the length of segment CB is equal to 4 square root of 10. By substitution, since AC is congruent to CB, then we can replace this CB by AC, and so we now have 2AC is equal to 4 square root of 10, and dividing by 2, we found that the length of segment AC is 2 square root of 10. So let's clear our figures so we can see what we found so far. What we have found so far is this length is 2 square root of 10. We know that this length here is x plus 1, and we already know that this length here is 2 units. So let's concentrate on this red right triangle at the top. Using now the Pythagorean theorem, we have the formula a squared plus b squared is equal to c squared. The length of A is x plus 1, so we now have the square of x plus 1 plus the square of our b, which is 2 squared, is equal to the square of our hypotenuse, which is the quantity 2 square root of 10 squared. Let's expand this square of binomial to x squared plus 2x plus 1. 2 squared is 4, the square of 2 is 4, and the square of square root of 10 is 10. Simplifying further, 1 plus 4 is 5, and 4 times 10 is 40. And then writing this in standard form, we have x squared plus 2x minus 35 equals 0. Factoring the left side and solving for x, we now found that x is negative 7 or x equals 5. Since we are talking about side lengths of geometric figures, we are going to rule out negative 7. This is an extra root, so we only accept x equals positive 5. And knowing now that x is equal to 5, we can now solve for the area of this smallest square. The area is 5 times 5 equals 25 square units. And knowing that the side length of the smallest square is x, the side length of the medium square is 1 unit more than x, or 5 plus 1 equals 6. And the side length of the largest square among the three is given by the expression x plus 2, where x is 5. So 5 plus 2 is 7, this length must be 7, and this length also here must be 7. So therefore, the area now of the medium square is 6 squared equals 36 square units, and the area of the largest square is 7 squared or 49 square units. For the total area, we get the sum of 25 plus 36 plus 49 square units to get 110 square units as the sum of the areas of these three squares. Now, at this point, if we interpret the question, what is the area of the three squares, to be the area of the three squares separately, without considering this overlap, then the total area is 110 square units. But if we interpret the question to be the total area of the three squares as drawn in this figure, then we have to subtract this overlap. And the area of this overlap is 2 square units, because we know that this side length here is 1 unit and this side length here is 2 units. So 1 times 2 is 2 square units. So subtracting this 2 square units from 110, then we will have the total area of this composite figure to be 110 minus 2 square units in order to get a final answer of 108 square units. But if we interpret the question to be the total area of the three squares separately without considering the overlap, then the answer is 110 square units. But if we consider the question to be the area of the three squares as drawn in the figure, then the answer is 108 square units. Suppose we are given this regular pentagon with a side length of 25 centimeters. It is also given that angle BFG, that means this angle BFG, is a right angle, and angle GAB is also a right angle. Point A is the center of the minor arc BE. What is the area of quadrilateral ABFG? A, B, F, and G. Now, what kind of quadrilateral is quadrilateral ABFG? From the figure, there are no parallel sides. So it's hard for us to fit any formula for the area of any type of quadrilateral in this case. So our next option here now is to check if it is possible for us to cut quadrilateral ABFG into several triangles in such a way that we'll be able to find the area of those resulting triangles. So what we can do is we can connect point B and point G like this and see if we can find the area of triangle ABG and triangle BFG separately. With that as our analysis, let's look at what are the other given in this problem. It is said that our figure ABCDE is a regular pentagon. That means the measure of this angle, D, and the measure of this angle C, and the measure of this angle B, and the measure of this angle A, and the measure of this angle E are all equal to 108 degrees. So that means the measure of each of these interior angles of the regular pentagon measures 108 degrees. You can check the properties of regular pentagon for this value, and we're going to use this later on in our solution. Second, it is given that point A is the center of minor arc BE. That means the length of side AB is equal to the length of side AG, which is also equal to the length of side AE. And since the pentagon is regular, then all those other sides I mentioned are also equal to side ED. And we know that the measure of side ED is 25 centimeters. So that means side AB is 25 centimeters and The measure of segment AG is also 25 centimeters. It is given that angle GAB is a right angle, meaning we can form this right triangle. We are referring to this right triangle. We know the length of this leg, we know the length of the other leg, then we'll be able to find the area of this triangle. So to find the area of the triangle, we use the formula area equals 1/2 times the base of 25 times the height of 25 also. The unit is in centimeters. This will give us a value of 312.5 centimeter squared. So we already know what is the area of this first triangle. Our goal is to find the area of the quadrilateral ABFG. So we are now halfway through our solution. Our next step now is to be able to know what is the area of triangle BGF. And if you can find that, we add these two areas and the problem is already solved. So next, how can we find the area of this triangle? What we know is angle BFG is a right angle. So we also have here a right triangle. We also know that this angle here, which is one of the angles of this pentagon, is 108 degrees. And we know also that this leg is equal to 25 and this other leg is equal to 25 and the angle here is 90 degrees. So what we have here is an isosceles triangle, and since the triangle is isosceles, the base angles are equal, and knowing that one of the angles is already 90, then it follows that this small angle here and this other angle here must be equal, and each of them is equal to 45 degrees. So that 45 plus 45 here is 90, plus the other 90 gives us a total of 180 degrees, which is the sum of the interior angles of a triangle. So, if you know that this angle is 45 and this bigger angle is 108 degrees, then we'll be able to find what is the measure of this angle here. That is equal to 108 minus 45, which gives us 63. The unit is in degrees. We're going to use these values later on. Next, if you know that this is 25 and this side is also 25, we'll be able to compute the length of this hypotenuse, knowing that the triangle is a 45-45-90 special triangle. And there's a formula to find the length of this hypotenuse, that side BG is equal to the length of the side, which is 25, times square root of 2. This from the properties of the special 45-45-90 right triangle. So knowing the length of this side, let's use a different color. And so by knowing now the length of this side is 25 square root of 2, and this angle is 63 degrees, and our triangle is a right triangle, then we can now use right angle trigonometry in order to find the area of this other triangle. So we need to know first what is the length of FG. Notice that with respect to this angle, which has a measure of 63 degrees, this is the opposite side, and BG is the hypotenuse. So sine of the angle 63 degrees is equal to the opposite side FG divided by the measure of the hypotenuse BG, which is 25 square root of 2. This gives us a value for FG to be equal to 25 square root of 2 times sine 63 degrees. Now sine of 63 is a constant times another constant. We know that this value is an exact number. Next, in order to find the area of this triangle, we need also the measure of this base. You can look at this as the height or the base depending on the orientation of the triangle, but we need the measure of side BF. With respect to this angle again, which has a measure of 63, this side BF is the adjacent side and BG is the hypotenuse, and that is computed by the function cosine of 63 equals BF over the hypotenuse 25 square root of 2. Now, let's continue our solution here. Solving now for BF. BF is equal to 25 square root of 2 times cosine of 63. So we know the length of BF, this length to be this value. And the length of FG, we computed earlier to be equal to 25 square root of 2 sine of 63. That is the value of side FG. So for the area of the triangle, area is equal to 1/2 the base times the height. And what is our base? The base is this value. This is the height. So area of the other triangle therefore is equal to 1/2 times 25 square root of 2 sine 63 times 25 square root of 2 cosine of 63. And using a calculator, this will give us a value of approximately 252.82 centimeter squared. And so we now know that the area of one triangle, this part here, is equal to this value, and this other triangle we computed earlier to be equal to 312.5 centimeters squared. So adding now this value plus this value, the area now of this quadrilateral, the combined area of the two triangles, is equal to 565.32 centimeters squared, rounded off to 2 decimal places. So that is how we solve this problem. The three overlapping rectangles at the right, colored pink, yellow, and green, are all congruent. And each of these rectangles has an area of 16 square meters. And they all meet at a singular point, P. The black dots mark the midpoints of the short side of the rectangles. What is the total area covered by this design? Let's analyze the problem this way. Let's focus on the given figure. Notice that in order to find the area of this design, we need to be able to find the area of these three kites. Let's highlight the three kites so that we can see it clearly. You have this red kite here, kite ABCP, and kite DEFP, and kite GHIP. What we want to find in this problem is the area of the design, particularly this design. But in order to find the area of that blue design, we need to be able to subtract from the area of the three rectangles these three red shaded kites. So what we want to find is the area of the design, and that area of the design is equal to the area of the three rectangles, and each rectangle has a given area of 16 square meters, and we need to be able to subtract the area of the three kites. And we do not know what is the area of the three kites. What we can do is we can extend this side and extend this side, and let's call this point as point J. Since we are given a rectangle, we know that this angle here is a right angle. We know that this angle is right angle. We know this angle also is right angle. The same thing here. This angle here is also right angle, and the same with this angle, because these are angles of the rectangles. Now, since the black dots are the midpoints of the shorter sides of congruent rectangles, then we can say that this side is congruent to this side, congruent to this side, congruent to this side also, congruent to this side, and congruent to this side. Now, since all these rectangles meet at this point P, which is the center of the three rectangles, we can conclude that this side of the rectangle also is divided into two equal parts, resulting to side CP being congruent to side FP, and side DP is also congruent to side IP, and side AP is also congruent to side PG, because this point is the midpoint of all these three rectangles, and since the three rectangles are all congruent, then dividing their sides into two equal parts would result to equal measures as well. Now, this angle is vertical to this angle, and therefore these two angles must also be congruent. Notice here that you have a straight line, and knowing that one of the angles of the two angles that form a linear pair is a right angle, then we can conclude that the other angle also here is a right angle. The same thing here, you have a line, and one angle is already given to be a right angle, then this angle here must also be a right angle. Now let's focus now on these two kites, kite ABCP and kite FPGJ. You have this angle congruent to this angle, you have this right angle congruent to another right angle, and you have this right angle congruent to another right angle. Since the three angles of one quadrilateral are congruent to the three angles of the other quadrilateral, we can conclude that their fourth angles must also be congruent in order for the sum of the interior angles to be equal to 360 degrees. What we now have here, therefore, are two kites with all their angles congruent, resulting for them to be similar quadrilaterals. But since they also have congruent sides, particularly this side, and all the other sides that are congruent, then we can now conclude that this kite ABCP, this kite, must be congruent to this kite at the bottom, kite PFJG up to P. So these two kites are congruent, and therefore we can now just transfer this kite at the top to this kite at the bottom in order to fill the space here. And let's shade that red also. So let's shade this as colored red as well. So that means we are now transferring this red shaded area to the bottom. And so in order to find the area of this design, we need to get the area of the three rectangles, and we are going to subtract this area, which is the area of the polygon DEJHI. We want to find the area of this red shaded part at the bottom because we already transferred this area to this part. But what is the area of DEJHI? Notice that we can find the area of this polygon DEJHI by starting from the area of the given rectangle here, which has an area of 16 square meters, and we can subtract the area of these two yellow triangles, so minus the area of triangle EKJ and the area of triangle HLJ. If we can find the area of these two yellow triangles, subtract it from 16, then we'll be able to find the area of this part. So let's do that. What we can do is we can connect these two midpoints and connect also these two midpoints. So basically we divided the rectangle into 4 equal parts. Notice now that this angle L is equal to this right angle here, because when you connect the midpoint here with the midpoint at the other side, and this midpoint here and the midpoint here, you are forming here a right angle, and that is congruent to this angle L. So also this side HL must also be congruent to this side here. So we know that this angle is congruent also to this angle. Now, since this part is the midpoint of side KL, that means that this length here must be equal to the length of the side here of the triangle. So using the side angle side congruence, then we can show that this triangle is congruent to this triangle here. And therefore, the sum of these two areas would be this area, triangle EKJ, which is this triangle, plus triangle EMJ, where the area of triangle EMJ is congruent to triangle JLH. So basically, the sum of these two triangles is this part, which we know is 1/4 the area of the rectangle. So if this is 1/4 the area of the rectangle, and the area of the rectangle is 16, then what we have here is 16 minus 1/4 times 16. Because this area is 1/4 of the rectangle. And this is now equal to 16 minus 1/4 of 16, which is 4. And so we arrive at an area of 12 square meters. This 12 square meters is now the area of polygon DEJHI, which is this polygon. So what we have therefore here is the area of the design that we are after is equal to 3 times 16, which is 48, minus this area, which is 12, and 48 minus 12 is equal to 36, and the unit is meter squared. So therefore, we have just computed that the area covered by the design, this part here until here, enclosing this design, must have an area of 36 meters squared. And that design now is this blue design. This is one way of solving this geometry challenge. What we have here is a circle and a square positioned as shown in the figure. The distance from the side of the square to the circle is 4 meters. The corner of the square and the circle intersect at only one point. The same thing here. The point of intersection is only one point. At the left side, the side of the square and the circle also intersect at only one point. Find the area of this square. You can pause the video and see if you can answer this geometry challenge. Okay, let's solve this problem together. At first, it appears that there seems to be insufficient given information because the only given here is this distance of 4 meters. We do not know the side of the square, we do not know the radius of the circle, and there's a lot of things that we do not know. So let's analyze this problem together. Let's construct this blue line segment, and when you extend that segment, it will form a diameter of the circle. From the center of the circle also, let's construct this line segment connected to this corner of the square, and this line segment becomes the radius of the circle. Now let's denote the length of this side of the square as x. That means this side also is x, and this side also is x. Since this line segment passes through the center of the circle, then this length of the triangle is equal to x over 2, or 1/2 the side of the square. Also, since the length of this blue line segment is x, and the distance between this side of the square and the circle is 4 meters, then the total length of the line segment would be this x plus this 4 meters. So we have here x plus 4, representing the diameter of the circle. Then, since this is the radius of the circle, then its length should be 1/2 the diameter. Since our diameter is x plus 4, then our radius should be 1/2 of x plus 4, and that is now this x plus 4 over 2, or 1/2 of x plus 4. So with respect to this right triangle, we now know that the hypotenuse is x plus 4 over 2. This leg is equal to x over 2. Let's find what is the representation of this other side of this right triangle. Let's take note from the middle of the circle up to this point on the circle, that is equal to the radius. And we know that the radius is this part. x plus 4 over 2. And we know also that this length is 4 meters. So if we subtract this 4 meters, then what we will have is the length of this side of the triangle. Therefore, this length of the side of the triangle would be x plus 4 over 2 minus this 4 meters. And that would be our representation of this side of the right triangle. So at this point, we now know that the length of the side of the triangle is x plus 4 over 2 minus 4. This length of the side of the triangle is x over 2, and the hypotenuse is x plus 4 over 2. So by knowing now the three sides of this right triangle, then we'll be able to compute for the value of x. Now, since we know the length of the three sides of this right triangle, then we can use the Pythagorean theorem. A squared plus b squared equals c squared. Here, our a is equal to x plus 4 over 2 minus 4, which we can simplify as 2 divided by 2 is 1 times x plus 4 is x plus 4. This is understood to be over 1. 2 divided by 1 is 2 times negative 4 is negative 8. And 4 minus 8 is negative 4. So we have x minus 4 over 2, which is now this part. And then raise it to the second power, which is now this exponent 2. Then our b is x over 2. So x over 2 raised to the second power equals, our hypotenuse c is x plus 4 over 2. So you have this x plus 4 over 2 raised to the second power. Then let's simplify this one. The quantity x minus 4 raised to the second power is x squared minus 8x plus 16. 2 raised to the second power is positive 4. Copy the plus sign. X raised to the second power, and then the denominator raised to the second power is 4. The quantity x plus 4 raised to the second power is x squared plus 8x plus 16. Then 2 raised to the second power is 4. Then we can multiply each of these terms by 4. And so we'll be able to cancel out all the denominators. And then what we have now is x squared minus 8x plus 16 plus x squared equals x squared plus 8x plus 16. We can subtract x squared from both sides, so this will be cancelled out. The same here, you have positive 16 and positive 16. By subtracting 16 from both sides, we'll be able to eliminate this 16. And what is left is x squared minus 8x equals 8x. And then subtracting 8x from both sides, we'll have x squared minus 16x equals 0. And from x squared minus 16x equals 0, we can factor out the common factor x to get x times the quantity x minus 16 equals 0. And therefore, x equals 0 or x equals 16. Obviously, x is not 0. X has a length, so we rule out x equals 0 as a root. And so we accept x equals 16. And if you know the length of the side to be 16, then the area of the square, therefore, is equal to 16 meters squared or 256 meters squared. So our answer is 256 square meters as the area of the square. Let's say we are given these different geometric figures composed of rectangle, triangle, a circle, and a semicircle. So in this figure, shapes of the same colors are congruent. That means this yellow rectangle is congruent to this other yellow rectangle. This equilateral triangle is congruent to this equilateral triangle. The rectangles are twice as long as they are wide. So if the height of this rectangle is x units, then the width of this yellow rectangle must be 2x. Since these two rectangles are congruent, the height here must also be x, and the width must also be 2x. If the area of the semicircle is 10, so this is our semicircle, the area is 10 square units, then we can extend this semicircle to form a complete circle. And the area below must also be 10 square units, so the area of this pink circle must be 20 square units. what is the area of the green circle? So we are after the area of this green circle at the top. So how are we going to find the area of this green circle given only these proportions of the sides and the area of the semicircle? What we can do is we can extend this line here so that we can enclose this circle with a triangle where all of those sides are tangent to the circle. By two-tangent theorem, we can prove that this triangle is an equilateral triangle. So basically, we have here a circle that is inscribed to this equilateral triangle. And we are going to do the same thing for this circle below. Now let's make our drawing clearer in the next slide. So we would like to enclose the bigger circle by this equilateral triangle and enclose also the pink circle below by an equilateral triangle. Let's continue extending these lines here. All these lines are parallel with each other, and also these other lines that are oriented going this way. And do the same thing for the circle below. And then for our dimensions, let's recall that the rectangle is twice as long as they are wide. So if this is x units here, then this distance here is 2x. Here is also x, and 2x also here. That means the side of this equilateral triangle is also x. That means this distance here is also x. That means this distance here is also x. Now you might be asking, it is not given that this triangle is equilateral. But notice that if you look at this triangle here, this triangle, this is a right angle here. With respect to this acute angle, the side opposite it is this height of this rectangle, which is x units, and the hypotenuse is this width of this other rectangle, which is 2x. So the ratio of the opposite over the hypotenuse is x over 2x, which is 1/2. And sine of what angle is equal to 1/2. Using our right angle trigonometry, we know that alpha here is equal to 30 degrees. And so if this is 30, and this is a right angle, 30 plus 90 is 120, then this remaining angle here must be 60 degrees. And so since we know that the side length of this triangle is x units, it must be x here because figures of the same colors are congruent. And we know also that this is 60 degrees. And this rectangle is divided into two equal parts by this triangle. So if this is x also here. And since the distance here is 2x, then the remaining part here must also be x. So x plus x is 2x, which is consistent here. And so you have now here at least an isosceles triangle with base angles equal. Since we know that this is already 60, the remaining two angles must have a sum of 120. And since these two angles are equal, each of them must have a measure of 60 degrees also. So we have an equilateral triangle. Now the next part here is we want to show that all these triangles that we form, this triangle and all these other triangles are congruent to this blue equilateral triangle. We can show that this angle here and this angle are vertical angles, so they are congruent. We know that this distance here is x, so that x plus x is 2x. By parallel lines cut by transversal, we can also show that this angle here is 60 degrees, and this remaining angle therefore must also be 60. Now since the triangle's equiangular and this distance here is x, then this side here must also be x, then this side here must also be x. So we have equilateral triangle again that is congruent to the original blue triangle. So that means we can show that all these triangles are congruent. Now let's take a look at the triangles formed by this pink circle. From the two-tangent theorem, we know that this point connected to this point of tangency here, and this point also connected to this point of tangency, must form equal distances here. We know that the height of this rectangle is x units, so this must be x here, and this distance here must also be x from the two-tangent theorem. And since the length of this rectangle is 2x, this remaining length here must be x, and from the two-tangent theorem, this must be x here also, up to this point. Now, since this is the diameter, if this is x units, and this line segment is perpendicular to the diameter, then this distance here must also be x, and from the two-tangent theorem again, this distance here must also be x. We know that this angle here is 60 degrees, it's 60 degrees here also, and it's also 60 degrees here. Why? Because we have equilateral triangle. This is a length of 2x, this is a length of 2x, this is a length of 2x, and this circle is inscribed to that triangle. So if this is x, and this is 60 degrees here, the remaining two angles here must be equal and must have a measure of 60 degrees each. So we have an equilateral triangle. This length here is also x, this length is x, and this is x. So we have just shown that all these triangles, this triangle, this triangle, this triangle, including these other triangles here, and this triangle at the bottom, are all congruent. And how many triangles are there at the top? There are 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 of those triangles, and the area of the green circle, let's denote it by A sub g. That ratio must be also equal to the area of the pink circle, which we know is 10 for the semicircle and 10 for the other semicircle at the bottom. So we have an area of 20 square units over the number of triangles formed here. So you have 1, we have this one, so you have 2, and here you have 3, and at the middle you have 4. So this is the first, this is the second, this is the third, and this is the fourth. So over 4. That means we can now solve for the area of the green circle by just solving this equation. So that means the area of the green circle is equal to 20 times 9 over 4. And solving now for A sub g, we have 20 divided by 4 is 5. 5 times 9 is 45 square units. So A sub g is equal to 45 square units. So this is how we solve this challenging geometry problem. The circumference of the blue circle is 10 units, and the perimeter of the red trapezoid is 15 units. What fraction of the trapezoid is shaded? So basically, when you look at this figure, we have here a circle that is inscribed to the red trapezoid. And so if we are looking for what fraction of the trapezoid is shaded, we want to know the area of the circle over whatever is the area of the red trapezoid. So we can analyze the problem this way. Let's look at what are the given. The circumference of the blue circle is 10 units. So C is equal to, the formula for circumference is 2 pi r, and this is equal to 10 units. It is also given that the perimeter of the trapezoid, P, is equal to 15. And the perimeter of the trapezoid is the sum of the 4 sides of this trapezoid. Let's recall that for a trapezoid, one pair of opposite sides are parallel, and the remaining pair are not parallel. And so if we call this point as A, this is B, this is C, and this is D, the perimeter of 15 is equal to the sum of AB plus side BC plus side CD plus side AD. And what we would like to know is what fraction of the trapezoid. So our denominator is the area of the trapezoid is shaded, and the shaded is the area of the circle. So we need to know what is the area of this blue circle, and we need to know what's the area of the trapezoid. And let's recall that the formula for the area of a circle is pi r squared, and the formula for the area of a trapezoid is the sum of the two bases, base 1 plus base 2 divided by 2 times the height. So how are we going to analyze this figure so that we can find this ratio? First, let's locate the center of the circle. And let's draw this radius perpendicular to side BC. Also from the center, let's draw this line segment that is perpendicular to this side. And let's do that here also. And let's do the same here. Now, this point A is a point outside the circle, and line segment AD and line segment AB are both tangent to the circle. Using now the two tangent theorem, we can now say that if we call this point as point E, this is point F, point G, and point H, then we can now say that the length of segment AE is equal to the length of segment AH. Let's call this length AE to be equal to X. That means this is also X here. The same reasoning is used for point B. Segment BA is tangent to the circle at this point E, and segment BC is also tangent to the circle at point F. So if we call the length of segment EB to be equal to Y, this is also Y here, and the same reasoning for the rest. Let's call this distance FC as W, GC is also W, and the length of segment HD as V, and the length of segment DG as V. That is because of the two tangent theorem. This distance from point A to this point of tangency E, and from this point E to the point of tangency H are equal. Now, using this two tangent theorem, we will now be able to find the area of this trapezoid. Area of the trapezoid is equal to base 1 plus base 2. Base 1 is this distance plus this distance, which is x plus y, plus our base 2 is this dg, which is v, and this distance gc, which is w. So we have v plus w. That's the base 1 plus base 2 divided by 2. So over 2 times the height. What is the height? The height is this distance, which is the radius, plus this distance, which is the radius. So we have 2r for the height. We can cancel out the 2. So what we now have is area of the trapezoid is equal to x plus y plus v plus w times r. But what is the value of x plus y plus v plus w? Notice now that the perimeter of the circle is the sum of all these distances. And what is the sum of those? You have two x's, you have two y's, you have 2w, and you have 2v. And this is equal to 15. So from here, we now have 15 is equal to 2 times x plus y plus w plus v. And therefore, we can now solve for x plus y plus w plus v to be equal to 15 over 2. So that means this part here is equal to 15 over 2 times r. We copy the r. So this is now the area of the trapezoid, and this is the area of the circle. So to find now the ratio between the area of the circle over the area of the trapezoid, we are now going to substitute 15 over 2r for this denominator. So let me erase this part here. So this is now equal to pi r squared divided by 15 over 2r, which we can also write as 15r in the denominator and 2 in the numerator. You have here a common factor of r for the numerator and the denominator, so this becomes 2 pi r over 15. But what is the value of 2 pi r? We know that 2 pi r is equal to 10. So this becomes 10 and copy 15, and 10 over 15 is 2 over 3. So our final answer is 2 over 3. The ratio of the area of the blue circle to the area of the trapezoid is equal to 2 over 3. Hi guys, Rolando Asisten here, and here is our math problem for today. We are given here 5 squares. The area of the green square is 12 square units, the area of the yellow square is 27 square units, 12 for the area of the red square, and 3 square units for the area of the pink square. We would like to find what is the area of this blue tupole square. You can pause the video and see if you can solve this CATRIONA Shearer'S puzzle. Now let's solve this problem together. Let's begin by noting that in order to find the area of this tupoled square, we need to be able to find the side length of the blue square. And in order to do that, let's concentrate first on the smaller squares. So let's isolate first the yellow square. If the area of the yellow square is 27 square units, then its side length is equal to the square root of 27, which can be simplified as 3 square root of 3. For the red square, the length is square root of 12 simplified to 2 square root of 3. And for the pink square, the side length is square root of 3. Now let's put back the other squares. Then let's concentrate on this right triangle. In this right triangle, the hypotenuse is the same as the side length of the blue square. The height of this triangle is equal to the sum of these 3 measures, and adding them all together, we found that the height of the triangle is equal to 6 square root of 3, because you have here 3 square root of 3 plus 2 square root of 3 plus 1 square root of 3. Then we are also interested in the smaller pink triangle. The height of this pink triangle is 2 square root of 3, but the base of the pink triangle would be the difference between the side length of this yellow square and the side length of the red square. Let's isolate these 2 triangles. We can now simplify this as 1 square root of 3, or simply square root of 3, and let's investigate the angles of these 2 triangles. Notice that I can put this pink triangle over here, and it shows that these angles of the green and pink triangles are congruent. The same with the angle at the top and the right angles. And so by AAA similarities, these 2 triangles are similar because their 3 corresponding angles are congruent. And since they are similar triangles, then their corresponding parts are proportional, and we come up with this proportion. The base over the height of the bigger triangle is equal to the base over the height of the smaller triangle. And solving for x, multiply both sides by 6 square root of 3, and simplifying further, we arrive at the value of x to be equal to 3 square root of 3. Now, by knowing the values of the 2 legs of this right triangle, we can now easily find the length of its hypotenuse by using the Pythagorean theorem. And so we now arrive at this equation. H squared is equal to the square of the first leg plus the square of the second leg. Solving for h squared, we arrive at 27 plus 108. And so finally the value of h squared is 135 square units. Now, do we need to find for the value of h? The answer is no, because we are after the area. And in order to find the area of this coupled square, we need to square the length of its side. And since we already have the squared value of the length of the side, this 135 is already the area of this blue coupled square. And so our final answer is 135 is the area of the coupled square. What we have here is a circle and 4 squares. The area of the yellow square is 400 square units. The area of this green square is 100 square units. And the area of this orange square is 64 square units. We do not know what is the area of this red square. Our goal is to find the area of this circle. In order to solve this problem, let's recall our inscribed angle theorem. When we have this circle with center at point O and draw this chord AB and chord AC in such a way that their point of intersection, point B, is on the circle, then the angle formed, angle ABC, is an example of an inscribed angle. And the inscribed angle theorem says that the measure of this inscribed angle is 1/2 the measure of the central angle AOC. In words, the measure of an inscribed angle is half the measure of the intercepted arc. In our case, the measure of the intercepted arc AC is equal to the measure of the central angle AOC. And corollary to this inscribed angle theorem, when we have a case where we have 2 or more inscribed angles with the same intercepted arc. For example, in this figure, we have this inscribed angle ADC and another inscribed angle ABC and another inscribed angle AFC. All of them have this common intercepted arc AC. Then our conclusion is angle ADC is congruent to angle ABC, congruent to angle AFC, because all of these 3 inscribed angles are subtended by the same arc AC. We are going to apply these theorems in order to solve our problem for today. So let's go back to our problem. One strategy in order to answer a problem like this is to redraw our figure in such a way that we are going to filter out information that are not important. So let's begin by looking at this segment AD, which is a chord of the circle. Since the yellow square is 400 square units, then we'll be able to find what is the length of the side of this yellow square. The length of the side is the square root of 400, which is 20. Similarly, since the area of this orange square is 64, then we'll be able to know what is the length of the side. The length of the side is the square root of 64, which is 8. We need those information, and in order to have some clarity about our figure, let's gather this important information in this circle at the right. So we now have this length of 20 units here and another length of 8 units. And together, we now say that the length of segment AD is equal to 28 units. Then let's look at this chord connecting point B to point C to another point on this circle. Since this green square is 100 square units, then we know that the length of segment BC would be the square root of 100, which is 10. So we now have this length of segment BC to be 10 units. Next, let's connect point B and point A in order to form this right triangle triangle BCA. And since the triangle is right triangle, and we know that the length of side BC is 10 units, and the length of side AC is 8 units, then we'll be able to compute what is the length of this hypotenuse BA. We can compute this using the Pythagorean theorem. So the length of side BA now is equal to the square root of 10 squared, which is the length of side BC squared, and 8 squared, which is also the length of side AC squared, which can be simplified as the square root of 164 and further simplified as 2 square root of 41. So the length of side BA therefore is 2 square root of 41. Next, let's connect point B and D in order to form this red right triangle, triangle BCD. In this red right triangle, we know that the length of side BC is 10 units and the length of side CD is 20 units. Therefore, we will be able to compute what is the length of the hypotenuse BD using Pythagorean theorem again. So here's our computation. The length of side BD is equal to the square root of this side, which has a measure of 20 units, so we have 20 squared, and this other side, which has a length of 10 units, so we have here 10 squared, which is equal to the square root of 500, or simplified as 10 square root of 5. Then, let's connect point B and point E in such a way that this chord passes through the center, and let's label the center as point O, and then connect point D to point E in order to form this orange triangle. To highlight the triangle, let's color the triangle red. Now, what do we know about this red triangle? Since segment BE passes through the center, then this segment BE is the longest chord or a diameter of circle O. This means that our circle is now divided into two semicircles. Each half of the circle measures 180 degrees. And since angle BDE is an inscribed angle, then the measure of this angle is 1/2 the measure of this semicircle, and so 1/2 of 180 degrees is 90 degrees. And so by inscribed angle theorem, we can now therefore say that this angle, angle BDE, is a right angle. And so we also have here a right triangle BDE. Another thing to notice is when you have this triangle BAD, with respect to this angle, angle BAD, its intercepted arc is arc BD. Also, with respect to angle BED, the intercepted arc of this angle also is arc BD. Since both these angles, angle BAD and angle BED, intercepted the same arc BD, then our conclusion is that these two angles are congruent from the corollary of the inscribed angle theorem. And so, we are now ready to compare triangle BAD and triangle BED by noting some of those congruent angles. So let's summarize what we know now. So consider triangle ACB and triangle EDB. We know that angle ACB is congruent to angle EDB because all right angles are congruent. Triangle ACB is a right angle. Triangle EDB is also a right angle. Next, we know that angle BAC, this angle, and angle BED, this angle, are also congruent because both these angles intercepted the same arc, arc BD. So from the corollary to the inscribed angle theorem, then angle BAC is congruent to angle BED. Next, we can compute that angle ABC is congruent to angle EBD. Angle ABC is this angle, and angle EBD is this angle. We can show that these two angles are congruent because we know that the sum of the interior angles of a triangle is 180 degrees. So if we know that the two angles of one triangle are congruent to the other two angles of another triangle, then subtracting the sum of those two angles from 180 degrees will result to these two congruent angles. At this point, we have just shown that the three angles of these two triangles, triangle ACB and triangle EDB, are all congruent. And so from these three statements, we can conclude that triangle ACB and triangle EDB are similar triangles. And when two triangles are similar, then their corresponding parts are proportional. And so we can now form this proportion. The ratio of side BC to side BA is equal to the ratio of the corresponding parts side BD to side BE. Notice that both AB and EB are the hypotenuse of the respective triangles, and BC and BD are the corresponding legs of these two similar right triangles. But we know that the measure of side BC is 10 units, and we know that the measure of side BA is 2 square root of 41, and the measure of side BD is 10 square root of 5. All of these measurements were computed from our previous slides, but we do not know what is the measure of side EB, and side EB is a diameter of our circle O. Computing now for the measure of side EB, we now have the measure of segment EB equals 2 square root of 205. And take note that this 2 square root of 205 is now the length of the diameter. And when we know the length of the diameter, we just divide this by 2 to get the measure of the radius. And so our radius therefore is 2 square root of 205 divided by 2, which is equal to square root of 205. And once we know what's the radius, it is now easy to compute for the area of the circle, because the area of the circle is pi radius squared, where our radius is square root of 205. And simplifying, the area is 205 pi. So therefore, our final answer is the area of the circle is 205 times pi. In decimal, that is approximately 644 square units. So here's the problem. We are given this parallelogram, and overlapping this parallelogram is a triangle. And when this parallelogram and triangle overlapped, three triangles are formed. We have this triangle with an area of 5 square units. We have this other triangle below with an area of 45 square units. And finally, we have this third triangle with an area of 20 square units. And our goal is to find the area of the parallelogram. So the parallelogram is this part. So how do you find the area of a parallelogram? Let's recall that if we have a parallelogram that look like this, the area of this parallelogram is given by the formula area is equal to the base times the height, where the base is this length and the height is this length. So if you're going to use this formula for this parallelogram, it implies that we need to find the length of this base, and this base has the same length as the other opposite side, and we need also to find the height, which is a line segment from one vertex of the parallelogram perpendicular to the opposite side. We can either find this height or we can draw that in the other side. But what we are given is the area. This 5 is not the length of the side of any of these figures, but 5 is the area of this triangle, this 45 is the area of the other triangle, and this 20 is also the area. So moving from area to length would require us to have a change of units, from square units to linear units. So one possible method is to use this formula. Another way that we can solve this problem is, since we already know the area of the triangles to be 5, 45, and 20, is there a way for us to tessellate the given parallelogram? When I say tessellate, we are going to cover the parallelogram by these smaller triangles, and we need to cover the parallelogram completely without overlaps. And if we can do that, then all we have to do is just count how many of these triangles can tessellate the parallelogram. And our task, therefore, of finding the area here is just counting how many triangles are there and multiplying that result by whatever is the area of that triangle. It turned out that this second method is the much easier way of solving this problem. So in this video, I'm going to show you how to solve this problem by tessellating the parallelogram with this smaller triangle. So how can we implement the second plan? First, we need to establish that these 3 triangles are similar triangles. And once we have proven that these 3 triangles are similar triangles, then we can apply the property that when triangles are similar, then their corresponding parts are proportional. And so, when the triangles are proportional, we'll be able to represent how many smaller triangles would there be inside this bigger triangle, and how many of the smaller triangle would there be in this other triangle. So let's proceed with the first task. So in order to implement the second plan, first we label the points of intersections. This point A, B, C, D, E, F, and G. Then let's recall that when you have 2 parallel lines cut by a transversal, the alternate interior angles are congruent. So in this figure, we can now think of this as parallel lines cut by this transversal. And because of that, this alternate interior angle here, which is angle BAC, and this angle here, EDC, must be congruent because of this theorem. We have the alternate interior angles theorem. Next, when we have 2 lines, the angles formed opposite each other is what we call as vertical angles. And by vertical angle theorem, these 2 vertical angles are also congruent. Notice here also that we have this angle and this angle to be vertical angles, and therefore they are congruent. So we can now say that angle ACB is congruent to angle DCE. Now, when the 2 angles of one triangle are congruent to the 2 angles of the other triangle, then the third angles are also congruent because the sum of the angles of a triangle is 180 degrees. So that means we can also conclude that angle ABC must be congruent to angle DEC. By the AA similarities, when the 3 angles of one triangle are congruent to the 3 angles of the other triangle, then the 2 triangles are similar. So we now say that triangle ABC and triangle DEC are similar. And our notation for similarity is this symbol. So we now know that this small triangle with an area of 5 square units is similar to this other triangle with an area of 45 square units. Now, let's consider these 2 triangles with an area of 45 and 20 respectively. So for these two triangles, immediately we already know that this angle is equal to this angle by vertical angle theorem. So we can say that angle CED must be congruent to angle FED. And then let's look at these two parallel sides. These two parallel sides are cut by this transversal. And therefore, this angle and this angle are alternate interior angles, similar to this. One at the right side, one at the left side, and both of them are inside the two parallel lines. So, we can say that angle CTE is also congruent to angle FGE. And when the two angles of a triangle are congruent to the other two angles of another triangle, then their third angles are also congruent. So we can now conclude that angle ECD is also congruent to angle EFG. So again, by the AA similarity, we can now say that triangle CED and triangle FED are also similar. So what we have now is this small triangle is similar to this bigger triangle, which is also similar to the third triangle. So the three triangles are similar. Now, since these three triangles are similar, then their corresponding parts are proportional. Let's look at the given areas. We have an area of 5 square units, an area of 45 square units, and an area of 20 square units. Now, since these three triangles are similar, then these areas must be proportional. Notice that there is a common factor here of 5. If we divide each of them by 5, 5 divided by 5 is 1, 45 divided by 5 is 9, 20 divided by 5 is 4. In here, when the proportion of the areas are in square units, the proportion of the sides are in the square root. So the proportionality now of the sides of these three triangles should be in the form square root of 1, square root of 9, and square root of 4, which are 1, 3, and 2. That means if the length of this side is 1 unit, for the other triangle it should be 3 units. We have to divide this part into 3 units. And for the remaining triangle, it's 2 units. We have to divide this part into 2 units. If this side is 1 unit, then for the biggest triangle among the three, it should be 3 parts. So we're going to subdivide this side into 3 parts, and the remaining triangle side should be divided into 2 equal parts. You have 1 and 2. Now, if this side is 1 unit, then for this biggest triangle among the three, this must be 3 units. And for the remaining triangle, this side here must be 2 units. What this will enable us to do is we can now form smaller triangles similar in area as this that can tessellate our parallelogram. So let's do that now. So this is now our approximate drawing of that. And if you're going to do this up to scale, it would look like this. So, what do we have now here? Notice that this triangle has the same area as this, the same area as this. So that means each of these small parallelogram is equivalent to twice the area of this triangle. So if the area of this triangle is 5, that means this is 10. So let's count how many like this are there all in all that tessellates or that cover this parallelogram. So you have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and then the other remaining 100 at the bottom. So this gives us a total of an area of the parallelogram to be equal to 200 square units. And notice now that this method is simpler than finding the length of the base and the height of the parallelogram, because we do not know how to find the height of the parallelogram. We know that the area of this triangle is 5, but we do not know what is this distance, and therefore we do not know also what is length. So to make our presentation much clearer, this is now the computerized rendering of this drawing. So thank you very much, and we hope to see you again in our next video.